So what I would like to do in this short lecture is really just use the opportunity to finish the discussion of substituent effects that we started in class on Wednesday, February 25th, substituent effects. And we can divide those effects into really two different topics to think about. So the first one is what effect the substituents have on the reactivity of the molecule. And the second one is what effect the substituents have on the regioselectivity. So again, let's just remind ourselves of the topic that we're talking about here. And this is if I contemplate doing an electrophilic aromatic substitution reaction on a regular benzene ring, and I compare that to doing the same reaction on a benzene that already has some kind of functional group on it. So here let's put in FG, that stands for functional group. And I want to do the same reaction now with an electrophilic aromatic substitution. The question now becomes, what effect does that functional group have, this FG, on the rate of the electrophilic aromatic substitution? How reactive is this molecule now that it has a functional group? And then secondly, I want to ask myself how the regioselectivity of this reaction is going to occur, meaning now if I want to add the E to this second reaction here, is that going to be in para, meta, or ortho relative to the functional group? So let's again label all of these positions so that it's clear and we know what we're talking about. And it's a little bit easier. Let's start with the question of reactivity of these molecules and how the functional groups affect the reactivity. And it's clear, I think, based on some of the discussions we've had in class, that generally when we talk about reactivity, the more electron withdrawing a substituent is, the more deactivating. Electron withdrawing substituents are deactivating, and electron donating substituents are activating. Okay, so now if I think about this kind of series of molecules shown here, if I start with nitrobenzene, so NO2, the chloro, the regular unsubstituted benzene, and the hydroxy, and I ask myself what are the relative rates of reactivity of these substituents to, in this particular example, a nitration reaction. So if I take all of these and I want to add another nitro group to the molecule, what are the rates of these reactions? Well, if I say take unsubstituted benzene, and I make that rate 1, then relative to that rate, the reaction of the hydroxyl group, hydroxyl substituted benzene, or phenol, here let's put that in here, the reaction of phenol is 1,000 times faster. The reaction of chlorobenzene is 0.033 times as fast. And the reaction of nitrobenzene to the addition of another nitro group is 6 times 10 to the negative 8. Okay, that's how slow and how deactivating this nitro group is compared to the reaction of an unsubstituted benzene, and especially compared to the reaction of a phenol. So here I'm talking about the reactivity of these substrates to electrophilic aromatic substitution. In general, and these particular numbers are for the reaction of these substrates to nitration. Now, in general, so that's as far as reactivity. And we're going to talk about why the reactivity is affected in a little bit more detail in a bit. The regioselectivity of the reactions are also affected by substituents that are already on the benzene ring. And what I mean by that is when I have this case of the functional group, let's zoom in up here. Here, this case over here, which is what I'm talking about, the identity of the functional group determines where the new electrophile is going to add. And in general, we can characterize functional groups as being either meta-directing, meta-directing, or they're ortho-para-directing. Alright, so things are either meta-directing or they're ortho-para-directing. And when I say ortho-para-directing, that means that the functional groups direct the incoming electrophile to both sites. Okay, so ortho-para-directing is not an either-or. That means both ortho and para sites see the electrophile. And you end up forming a mixture of the ortho-para and the of the ortho and the para directed products. In general, functional groups that are deactivating are meta-directing, and functional groups that are activating are ortho-para-directing. Let's write that down. In general, functional groups that are deactivating are meta-directing, and functional groups that are activating are ortho-para-directing. The only exception to this is the halogens. Halogens are weakly deactivating, but ortho-para-directing. And you can go to your book, this is figure 1611 in the book, has a chart of the summary chart of how different functional groups affect the reactivity and the regioselectivity of these reactions. So here's a picture of it. So if I look at benzene over here, all of these electron donating groups are activating, so they're more reactive and ortho-para-directing. All of these electron withdrawing groups are deactivating and meta-directing, and here these halogens I'm showing they're weakly deactivating, so they're less reactive than benzene, but not by a lot, and they are also ortho-para-directing. Now let's talk in more specifics about how different functional groups activate and deactivate the benzene ring towards further electrophilic aromatics. Alright, so now let's talk in more specifics about how different functional groups can be activating or deactivating. So let's start with the three cases shown up here. Alright, where this Y here is electron withdrawing. Let's put an arrow here, that's a good arrow, which means that before I start introducing reactivity, this molecule, this functional group is already withdrawing electron density from the aromatic ring. Alright, and this is our regular unsubstituted benzene reference, and this guy here, this X, is electron donating. Alright, so that's going to be putting electron density into the aromatic ring. Alright, now let's ask what's going to happen when I react each of these with some kind of generic electrophile, call it an E+, for example. So these are all going to undergo the same reaction with an E+, and they're all going to form analogous intermediates. So, for example, in this case, in the unsubstituted benzene, I add an electrophile to this carbon, that's this E. I then form a positive charge on the carbon that is adjacent to it. Alright, so this is my carbocation intermediate. And similarly here, I put the E on this carbon and put a positive charge on the carbon adjacent to my incoming electrophile. Same here. E goes on the top carbon, positive charge goes over here. Let's now think through what happens to the stability of this molecule when this Y is withdrawing electron density away from an atom that already has a positive charge. That makes it less stable, destabilizes the carbocation, compared to a case where the X is pushing electron density into that carbon. The carbon with the positive charge is getting electron density here pushed into it. This is going to stabilize the carbocation intermediate and in turn activate the ring for electrophilic aromatic substitution. And we can even divide this into two different categories of activation and deactivating. We can separate out what are called inductive effects, and the other choice is to talk about resonance effects. Okay, so there are two. This is within the category of figuring out why are things activating or deactivating. We can talk about both inductive effects and resonance effects in this particular case. So inductive effects refers to electron density along a sigma bond. Inductive electron effects along a single bond. So that's sort of what we're talking about over here in the top case. If I have an electron withdrawing group that pulls the density along this sigma bond, if I have an electron donating group that pushes electron density again along the sigma bond to stabilize that particular carbocation. And that really, these inductive effects are really a result of electronegativity difference. So they're determined by electronegativity differences, all right? And what I mean by that is a nitro, a halogen, a hydroxyl, even anything where I put a heteroatom on this aromatic ring, that's going to have the effect of pulling electron density away from the benzene ring, again because of the electronegativity differences between the carbons and these heteroatoms. So I'm going to put, for example, this OH here. This OH guy is inductively withdrawing. So all of these are inductively withdrawing because of meaning they're withdrawing electron density along this sigma bond because of the electronegativity differences. So that's as far as inductive effects. The other effect in talking about activating and deactivating are what are called resonance effects. All right, and those relate to the withdrawal or donating electrons through pi bonds. Okay, so this is electron effects along pi bonds. These occur in cases where, so you can have resonance donating where the lone pairs can donate to form pi bonds. Those are resonance donating. So these can either be resonance donating or resonance withdrawing. So let's see, resonance withdrawing effects first. Let's show an example of that. And this would be resonance withdrawing. Would be a good case to look at would be this kind of carbonyl, these acyl groups here. So let's put on an acyl group, and this can be withdrawing electrons along a pi bond, for example, by drawing a resonance form like this, and then here, where along the pi bond system I could end up drawing a resonance form for this molecule. Hold on, that looks like this. And what I've done when I draw a resonance form this way is I've created a positive charge in the aromatic ring, all right, and that's withdrawing by certainly by inductive effects for this carbonyl because this oxygen is electronegative, but also resonance effects. So this is, I can withdraw electron density along a pi bond in cases where I can draw a resonance form using pi bond migration to put a positive charge on the benzene ring, that's now resonance withdrawing. I can also have resonance donating effects, and these are potentially more useful or interesting, and that's going to be in cases where there is a lone pair on an atom directly attached to the aromatic ring. What that allows me to do is generate, now here let's pick OH as a good example of that. If I put a lone pair, if I put an oxygen here with a lone pair on that oxygen molecule itself, on that oxygen atom, I can now draw a resonance form that puts and pushes that electron density, again via pi bonds formation, into the aromatic ring. So that's what I'm going to try to show here, where now using pi bonding of this molecule, I can draw resonance forms with electron density, in this case a full negative charge, in the aromatic ring structure. Now I'm going to have a positive charge on my hydroxyl group over here, but anything that has an atom, a heteroatom with a lone pair directly attached to the aromatic ring, that's going to be resonance donating. Anything like these carbonyl groups where I can draw resonance forms to push electron density out of the aromatic ring, those are going to be resonance withdrawing. And again, these effects act in concert with the inductive effects of things donating or withdrawing along the sigma bonds. I can now also begin to look at things being donating or withdrawing along pi bonds, and the total effect that a substituent has is a combination of inductive effects and resonance effects. So for example, in this particular case, carbonyl groups are both inductively withdrawing and resonance withdrawing. So those are overall resonance deactivating groups. Hydroxyl groups, on the other hand, are inductively withdrawing. That's because the OH is an electronegative atom, but resonance donating, and overall they are activating. That's because the resonance donating effect dramatically overwhelms the inductive withdrawing effect. Halogen atoms are inductively withdrawing and are also resonance donating. Here they end up as weakly deactivating. That's because the inductive withdrawing effect in this case is mildly stronger than the resonance donating effect in this particular case. So again, we can talk broadly about substituents being electron donating or electron withdrawing. However, we can then, sort of as a secondary level of understanding, break this out into into inductive effects, that's the electronic effects along sigma bonds, and resonance effects, which is the electron effects along the pi bonds. What we can also do is look now at the particular functional groups and how they affect the regioselectivity. So let's go back now to the regioselectivity effects and start talking about specific groups. So in particular, let's start by looking at toluene as an example of alkyl groups. Okay, so alkyl groups are activating and ortho-para-directing. If I look now at toluene, okay, so let's write toluene here. Yes, you are responsible for knowing the name of toluene, of phenol, of the things that we refer to, sort of the common aromatic groups. And I want to add a nitro group to the toluene molecule. So let's do this particular electrophilic aromatic substitution reaction. That's to add an NO2 group to my molecule. Alright, and this is my electrophile here. I can now add it in to form 3 different carbocation intermediates. So the first one is going to be, now if the nitro group adds ortho to the toluene, ortho to the methyl group, let's put that over here. If it adds ortho to the methyl group, so here's my methyl, I put the NO2 over here, that results in a positive charge on the carbon that has the methyl group. Again, so I put the nitro group on this carbon, I now have a positive charge over here. Alright, I can also think about adding a nitro group to the meta position. Alright, so the same reaction now, just with different selectivities. Let's see where that results in my nitro group now. If I want to add the nitro to the meta position in this particular case, let's put the nitro group now on this position, so now this is meta. That results in a positive charge now on this carbon. So if this is the bond that's involved in the electrophilic aromatic substitution reaction, what that means is the nitro group adds to one side and the positive charge ends up on the other side. So that's the meta. And then finally I can think about adding the nitro group in a para position to where the methyl group on the toluene is. And if I do that case, then what that gives me now again is the nitro group on one side of the double bond that's involved in the addition, and the positive charge on the other side. So for this particular case, now I want to add the nitro group para, so let's put that in over here. Hold on, let's put that nitro group there. And if this is the bond that was involved in forming the reaction, that now puts a positive charge over here. So again, these are the 3 possible intermediates that I can get from doing a nitro addition to toluene, so to ortho addition or meta addition or para addition in this case. And we can now ask ourselves, what is the most stable carbocation intermediate? And that's going to be driven by in which cases can I get a positive charge on the carbon that has the methyl group on it. So the most stable carbocation is the one with a positive charge on the methyl substituted C. Alright, so that's again because the methyl group is electron donating. That means that when I have a positive charge here on this carbon, that's the most stable. So certainly ortho is a very stable carbocation, but what I can do is draw resonance forms for these cases and see whether I can resonance stabilize a positive charge, sort of like to move that positive charge along to get it to be on that methyl group. So here I can draw a resonance form. So this para substituted group, now if I just do a different resonance form here, I can move the positive charge onto that carbon, and that works out well to give me the positive charge now in the most stable position. Alright, so that's again, even though the ortho, the most stable carbocation is the one with the positive charge on the methyl substituted C, so that I see in this case. In the para case, that positive charge does not initially start on that C, but it's very easy for me to draw a resonance form to put the positive charge onto that carbon, so that's what I see over here. If I now contrast that with the case of the meta substituted situation, alright, so that's this guy here, I can draw resonance forms on this intermediate pretty much indefinitely till I'm blue in the face, and that's never going to, there's no resonance form that I can draw from this meta substituent that is going to put the positive charge where I want it to be. It's always going to keep sort of skipping around the ring in a way that makes it not stabilized by the carbon of the toluene, this methyl group over here. So I can resonance it over here, I can resonance it over here. I can never resonance and get that positive charge where I want to, which is now why the alkyl groups that are activating and electron donating only direct nitro or whatever substituents or whatever electrophile to either the ortho position, because that puts the positive charge directly on the extra stabilized carbon, or the para position, because that can easily be resonated to be stabilized on this carbon, but never to the meta position. So that's as far as why alkyl groups are ortho-para directing. I want to talk now specifically about why phenols and why OH groups and NH2 groups are ortho-para directing. Alright, so they, again, just to remind ourselves, based on the activating deactivating discussion, these are inductively withdrawing but strongly resonance donating, so that's why they're overall activating overall and ortho-para directing. Alright, so let's go through why that is the case. If I look at phenol, for example, okay, so that's this compound here, this OH phenol, and I look at adding a nitro group to this compound, I can again do the same sort of discussion that I had for the case of toluene, by which I mean, let's see what the resonance forms are for adding ortho and meta and para. Alright, so this top one will be for ortho addition. This will be our meta addition. This will now be the para addition reaction. Alright, so now if I want to add this nitro group ortho to the phenol, what that gives me is a positive charge on the carbon that has the OH. If I add it meta, I can do the same sort of analysis to put a positive charge on the carbon that's now para. Alright, and then finally if I add para, what that lets me do is put a positive charge here on the meta position. And again, these are going to have both the ortho, obviously, and the para can give resonance forms where the positive charge is actually on the carbon with the OH attached to it. Alright, so I can draw a resonance form for this para substitution reaction here, in which case the positive charge has now moved onto this carbon. Alright, so this is a resonance form of the para substitution reaction. And what that lets me do for both, here I'll highlight in red the ones that I'm talking about in particular, for this guy and for this, once I get the positive charge onto the carbon that has the OH, that gives me an additional stable resonance form where now the lone pair of electrons in the oxygen can act to create additional resonance stabilization. So that's what I'm going to show here as well, and this is exactly because of the resonance donating effect of the hydroxyl group. Again, so because I have these lone pair of electrons on the hydroxyls that are directly attached to the positive charge, that lets me create a situation like this where now the OH group is the one that's in charge of bearing that positive charge, and that additional resonance stabilized form that I have for the ortho and the para case So this is additional or an extra resonance stabilizing form that I have for the ortho and the para case is a result of the resonance stabilization because of the lone pair of electrons on the hydroxyl groups, okay? And that's what makes these particular groups the same analogous for the NH2 case. These particular groups, OH and NH2, are going to be ortho-para directing again because of the resonance stabilization that I get in this. Now, halogen atoms are deactivating, okay, and they're deactivating because the electron withdrawing inductive effects are greater than electron donating resonance effects. However, they are still ortho-para directing because they, like these OHs, have the lone pair of electrons that they can use to form extra resonance forms. So I'm just going to show one case of that. I'm not going to go through this for every case, but here, for example, if I have Cl and I add an ortho-nitro group to there, what that lets me do is create a positive charge on the halogen-bearing carbon, all right, so that's here, and NO2, and I put a positive charge right there. I now have a lone pair of electrons on this chlorine that can stabilize that resonance form, and again, that additional resonance stabilized form is only available in cases where the nitro group is now going to be in the ortho or the para position. All right, so this is sort of just an analogy of the OH and the NH2, but that's why the halogens are ortho-para directing, even though they are deactivating. All right, and then the final case are meta deactivators. For example, acyl groups are deactivating and meta, and that's precisely for the opposite, exactly the opposite case as these electron donating ortho-para groups. For example, if I want to do this over here like so, what I don't want, and I specifically do not want to end up with a positive charge on the aromatic, don't want a positive charge on the carbon that is attached to the carbonyl group. I specifically do not want that to be the case, and that's why they end up with meta substitution patterns. So let's just draw a meta reaction over here, and the meta reaction works because now if I put something meta, that gives me the positive charge right over there, and there is no way for that positive charge to end up through resonance on this carbon, which is exactly what I want. So that's why the electron withdrawing carbonyls and nitros and other such things, those are all meta directing again because we specifically want to avoid having a positive charge on the carbon that bears those electron withdrawing substituents. Alright, so that concludes the discussion of substituent effects in electrophilic aromatic substitution reactions. Alright, that's sections 16.4 and 16.5 in the textbook, and there will be practice problems about this online lecture as well. I'm going to divide the chapter 16 problem sets to be focused on these particular lectures.